Okay, so we're working on logarithms. So this is probably a different approach than maybe if you've learned logs in the past, but it's better. Trust me, it will give you a lot more ability, and it'll pay dividends when it comes to exponential growth and dealing with logs. If you can learn it this way, it will really pay off, okay? So here, this was the thing that we said. It's not that just logs are this way of solving for exponents. Logs are exponents, okay? That's what they are. So when you look at a log with numbers on it, it's about identifying what exponent it's talking about. That's the point. What exponent is it talking about? So, and here's the great thing that makes it easy. You can just read it from left to right. You can just read it from left to right. So we say that x is, what's a log? Exponent. So x is the exponent of b that will equal or give a. That's right. So you can just read it from left to right. That's how you can remember it. If you can remember and understand this, you never have to memorize anything. You don't have to memorize, where do I put this number and where do I put this number, okay? It's just about knowing what a log is. X is the exponent of b that gives a. So if you understand that worded statement, then this is a piece of cake. X is the exponent. Where does it go? It goes to the exponent. The exponent of b. Where does b go? On the left. Yes, x is the exponent of b. That gives a. You see? So what's the meaning of that? What's the meaning of that? Diana, what did I just write up there? Okay, so and to what power? So what is this? What is a log? Yeah, Taylor.
Log are exponents to the power of x equals 10.
Okay, that's right. How can we say this in words? What is this thing that you're looking at? The exponent of 2 that will give you 10. The exponent of 2 that will give you 10. So they both said that means that, so if we called it, say c, then c is the exponent of 2 that would give 10. So c is the exponent of 2 that would give you 10. All right, so can you approximate what exponent that is? Can you, maybe just before we do any calculations, can you give a shot? What is it about? So we know what's 2 to the 1. 2 squared. 2 cubed. 2 to the 4th. So what would you estimate that exponent of 2 to be that would give 10? So something between 3 and 4, right? Closer to 3 or closer to 4? Something, yeah, so like maybe we could guess, or a guess would be 3.3, 3.4? We'll say, oh, that's a pretty good guess. How'd you get it? Are you seriously guessing?
Well, if you take 3.4 and 3.3 and average it, you get 3.3.
Oh, okay. That's slick. Okay. All right. Okay, so let's really find it now. So so your calculator doesn't have a button. It doesn't have a single button for log base 2. But it does have log base 10 and log base e. So log of 10, this is this change of base formula. It's a formula that gives you an equivalent way to write that log. You can change it to any base you want. So you can do ln. Or I could do log base pi of 10 over log base pi of 2. Doesn't matter. You can choose any base that you want. Since we're using our calculator to do it, we're going to use one of the two that you have built in as a button. Who's got it? 3 point what? 3, 1? 3, 2, 1? And that's an approximation itself, so that will keep going. Okay, 3.321. Our guess was 3.3, 3.35, whatever. Does it make sense? Okay, so in words. In words, tell me what that is. What did I just write? The meaning of that in words. Jimmy. He's saying that whole thing is the exponent of 10 that gives 95. All right, so so let's call it P. So if P is the exponent of 10 that gives 95, then how can we write that out? Michelle. Yeah, so this is the exponent of 10 that gives 95. We called it P. So 10 to the P is 95. All right, let's guess this one. 10 to the 1 is? 10 squared is? So, guess what P is? 1.9. Yeah, closer to 2 than to 1, right? So it's almost 100. And we know that the exponent of 2 of 10 gives 100. Okay, now let's find it. So now this is one that's just built into your calculator, right? So if there's nothing there, it means base 10. What is it? 97? 97. Give me one more decimal place. Do I have it right? 1.977 is the exponent of 10 that gives 95. That's what log 95 is. The exponent of 10 that would give you 95. Okay, so it's a log. It's a special log, so we just need to know what the base is. When you see ln, that's just like a normal log with a special base. What base? E, okay? So this thing, ln of 0.45, what does it mean in words? What does it mean in words? ln of 0.45. Frank. He's saying that this ln of 0.45 is an exponent. It's the exponent of e that would give you 0.45. Is that right? Yeah, so we'll call it z. How would you rewrite it in terms of z? Fernando. Yeah, so z is the exponent of e that will give you 0.45. Logs are exponents, okay? Just by looking at the numbers, you know exactly what exponent it is. All right, again, your calculator has that. What is it, negative what? 98. So e to the negative 7.98 is 0.45. Okay, so where this comes into play is when we have equations, let's say y equals 4 to the x. And we say, what's y when x is 120? So what's y when x is 120? So obviously we're going to say that y is 120. And now we have a tool to know exactly what x is. So Anthony, in words, what is that exponent x? What's that? Oh, yeah, sorry. My fault. If you were confused, that's good. That's what I meant. What's x when y is 120? That's what I meant. So we plug in 120 for y. And so now what? We need the exponent of 4 that gives 120. How do we rewrite that? Log base 4 of. So watch out for saying log of 4 to the 120th. That's a common thing that students want to do. They say log of 4 to the 120th. No, it's log base 4 of 120. Again, the exponent of 4 that will give you 120. All right, and so we need the change of base to do this. So I'll use just ln this time. ln of 120 over ln of 4. We never showed where that formula came from. We're just using it, okay? We're just using it. We never showed where it came from. Shout it out when you get it. 3.45? 455. Doesn't work. One person, nice and loud.
3.45.
One more decimal place.
3.
3.453. Thank you. Okay, another example. Question, sorry. Because the change of base formula, this also equals the log base 121 of 120 over the log base 121 over 4. The change of base formula allows you to choose any base that you want. You can choose anyone. So you can do ln, you can do log base 10, but you're going to choose one of those because that's what you have a button for. Out of my hat. So it's also equal to log of 1.8. Log base 1.8 of 120 over log base 1.8 of 4. Do you get it? It's any base you can choose. Choose any base that you want. Okay, another example. Z equals 30 e to the 1/4 x. Okay, what's x when z is 1079? Okay, so we're trying to solve for an exponent because x is in the exponent, but we got some layers to remove here. We gotta apply, change it to log at the right time. We gotta change that exponent to log at the right time. So it's not ready yet because we've got this 30 times this exponential term. So the first step is to get that exponential term by itself, which means piece of cake, right? Divide by 30. So the question is, are we now ready to change this into a log? Yeah, it's just that now this whole thing is the exponent. But that doesn't scare us. We just treat it as one unit, okay? Just treat it as one unit. 1/4 x is the exponent. So now, if 1/4 x is the exponent, what log is it? What log? If it's the exponent, then what log is it? Yeah, ln. So ln or log base e. It's the exponent of e that gives z over 30. It's the exponent of e that gives z over 30. And some of you said that's ln, right? Exactly. Oh, but we know what z is. I didn't put it in, sorry. So all along here we knew what z was, 1079. Okay, so this over here we have the natural log of 1079 over 30. Someone get it? What is that?
3.58.
Oh, 3 is our favorite number today. 3.582. And so we want to know what x is. 3.582 is 1/4 x. Therefore, I'm going to multiply both sides by 4 to get x isolated. So you're going to get to, what, 14, 15 something? What?
14.330.
33, thank you. So does it make sense? In order to use log on something like this, you got to get that exponential term by itself. And then if you have an expression there as the exponent, it doesn't matter. It just treat it as that's the exponent. It's, what is it? The exponent of e that gives that number. So we write it this way. The exponent of e that gives that number. And exponents of e are written as natural logs. Natural logs are exponents of e. Okay, so, and then let's just quickly review. Any questions on that? So every time you have a log in a problem, whether you're creating it or it's in front of you already, practice this thing. Practice saying what exponent it is in words. Okay? I'm telling you, that will pay big dividends because then you don't have to memorize anything. And you understand what logs are. You really grasp what logs are. They're an exponent, and those numbers tell you exactly what exponent it is. So just keep practicing that. Keep practicing using this phrase. Oh, that log is the exponent of this that will give this. Okay, quick review. First class. We're going to do number 67 together. Right there. Okay, so 67 says we've got this investment, and T is the number of compounding periods. So it's a real general problem. We know that we can get a lot more detailed with compounding, but in terms of years or months. But they're just letting T be generically the number of compounding periods. Okay, and they said, when will this investment reach $1 million? When will it reach $1 million? So, where would we find 1 million in this expression if we're asking when it's going to reach $1 million? He wants 1 million to be f of t. Right, it's the output. So we're asking after how many compounding periods will the output or the amount of money reach 1 million? Okay, so we'll go 1 million equals 4186.58. And our goal now is to solve for t. So up to this point, we said graph it and find where y is 1 million and get the x value, right? So, but now we've got the tools to do this without a graph. We can do it with algebra. So we know we want to solve for exponent. That means we're going to apply. Exponents are logs, right? So are we ready to apply the log? First step is we got to get that exponential term, this 1.025 to the t, by itself. We've got to isolate that. Okay? First step is to then divide this 1 million by 4186.58. And that will equal our 1.025 to the t. Okay, let's get that value. One person, nice and loud. 1 million over, oh, I can do it right here.
238.86.
86, you beat me. And I agree. Oh, did I do it wrong? I got 238. I got 238.86. Is that what you said?
Yes.
Sorry. 238.86 is 1.052 to the t. And now we know exactly what t is. We just write it down. Let's see here. What will t be? Austin. The exponent of 1.025 that gives, or of, right? We're not, yeah, so it's an easy mistake to make because this is down lower and this is not the exponent of this. It's easy to think that because the way it's set up. But this is not an exponent of this. So the whole thing is the exponent of 1.025 that gives 238.86, which is exactly what we want right there. How are we going to solve that? We don't have a 1.025 button, log button on our calculator. So we'll do log this time. 238. I got 221.76. Okay, so now we've got all this stuff, and we don't want to lose sight of what this means. What does this number mean? Is that dollars? Is that days? What is that? Number of compounding periods. We were solving for how many compounding periods it took to get to 1 million.
Would we, in like a test or question, would we round that to 222?
Yeah, so to truly get to 1 million compounding periods, what is it going to take? Yeah, so it's either going to be 221 or 222. What gets us to 1 million? Yeah, got to go up. If it were 221.1, how many compounding periods would it take us to get to 1 million? Still 222. Because that would mean that at 221, we're shy of 1 million still. Right? So 222 compounding periods. Okay, so now what I want you to work on is, first of all, 71. But let's talk, I'm going to talk about that first. Any questions on number 67? So for number 71, we've got this other form. So remember, we have two forms of exponential growth now. We can look at it the old way we did it, and then this new way. What do we call this new way of modeling exponential growth? What was this about? Continuously, right? Continuous. Yeah, and the others, so the old way that we had was? Well, they're both exponential. They both model continuous exponential growth. It's just that we had this old form, a b to the x, and now we have this new form, which is a e to the r to the x. Okay? Let's review this number. What is this number right here? What do we call that number right there? The growth rate, the growth factor. What is it? It's not a growth or decay factor. This is called the continuous rate. So this is from Wednesday. We went over this. Hopefully I didn't lose that PowerPoint. But this is called the continuous rate. So by negative 0.13, every unit of n is this quantity decreasing 13.16 per unit of n. Is that what that's saying, the continuous rate? I see a yes and I see a no. Do you remember from Wednesday? The continuous rate. Remember I said this is a hard thing for students to get. Does this reflect the actual change per unit of n? No, it's just not. Continuous rate is not the actual percent change. We have to relate it back to this to get the actual percent change. Okay? So that's your, just to prompt you to get you started. So before doing the actual questions in 71, A through D, or just A through C, before doing that, I want you to find the actual percent change per day in this question. This is about the size of a wound. So find the actual percent change of the size of the wound every day if the continuous rate is negative 0.1316. And then answer A through C on 71. Then if you get done with that, work on 73. So you need your own paper, your own notes, because this is in the homework section, and you don't have room to write in there. So complete these in your own notes. So 71, first answer this question: what's the true rate of decrease as a percent? And then do A through C, and then do 73. Is the task clear? Okay, so Roy can circle around and help you out. Okay, so for part B, it's asking for the size at a particular number of, or at 1 week. So what will our input be? We got to know for sure what the input of the original function is. N is the number of days. Input for 1 week? 7. Okay, so that's easy. You just should be able to get that value easy. Should be something less than 300. What is it? Like 113? 119. Okay, something about 119. Okay, C says now we want to know how long it takes to get to 30% of its original size. So first we need 30% of that original size, which is 90. So we know that we're getting a log. We know that we're going to use a log to get this value of n. Are we ready to do that? No, this is not written correctly, sorry. This is e to the negative 0.136. So we need to isolate that exponential term before we can apply log to get that exponent. Do I have it right? So you're going to divide by 300, which gives you 0.3. So there's our 30%. Okay? So how are we going to, so just, again, that's an expression. Just keep it as a unit. And that whole unit together, that whole thing in red, is the exponent. So we're going to write that. Write that whole exponent. What exponent is it? Natural log, because it's the log base e, or the log, or the exponent of e. The exponent of e that gives 0.3. Read it left to right. The exponent of e that gives 0.3. The exponent of e that gives 0.3. And as many of you are saying, that's natural log. So to solve for n, we've got one more step. Divide by that. So it's the natural log of 0.3 divided by. And so this whole thing is like 8 or 9 days or something? 9.14 days. Is what you should have gotten when you did that. Okay, so some of you from a past course, you have this security blanket. And that security blanket is take the log of both sides. Okay? This actually is less work. It saves you a step or two. So from this step right here, to rewrite that exponent as its equivalent log, just saved you a step. Okay? So, and I recommend that because this really means you have a grasp of what a log is, rather than, oh, I just learned to put these symbols here and move this here, and then I can do the algebra, right? So use your understanding of logs to solve it, and it actually saves you time, saves you a step. This is the exponent of e that gives 0.3, so write it as a log, the exponent of e that gives 0.3, which is the natural log. Questions on number 71? Okay, so if you haven't started yet, so work on 73. And then for part A, start by writing part A. Let's go back here. We never did the percent increase. So let's go back and do, this is the important thing. For that original function there, I asked you, what is the true percent decrease if it's not 13.16? What's the true percent decrease? So how do we get started with that? Well, we have to compare it to our old a, b to the x. So how are we going to get started to figure out what the true percent decrease is? Anyone get it? That's it. Because remember this, here's our starting value, those agree. And we got the exponent input, those agree. So what's left? The base of is b is equal to e to the r. That's the key to get from this continuous rate to the true rate of change. Okay, and what is that? What is the value of b? 8.7. Can I do 877? Okay, 0.877. What does that number mean? So what is 0.877? What's that? She said that's how much you keep. Actually how much you keep? Right, per unit is actually how much you keep, because that's the true B. We got decay, so this is the true decay factor. It's the true decay factor. And so if we keep that much, how much do we lose? So we know 87.7% is one of our percentages. 12.3 then is the rest that gets us to 100. So that's the true percent decrease. Did you catch it? It's not 13.16 decrease. That's the continuous rate. We need to combine that with continuous compounding to get the actual true rate of decrease. So here's a kind of a tougher question. If the continuous rate is 13.16, why is it that when we combine it with compounding, we get a lower percent decrease, actual. Shouldn't it have been higher? If we're going to take that and combine it with compounding, we're going to take the 13.16, and now we're going to compound it every moment, but we got a lower percent decrease. What's that? Yeah, so why? It's because of decay. Why with decay do you get an actual percent decrease that's less than your continuous rate? Yeah. What's that? Okay, but what's happening? What's happening that results in an actual lower percent decrease? Yeah.
Well, it was taking away for continuously the 13.16%.
Okay.
So that means that the true decay factor, what they're left with.
This is a hard idea. This is a hard idea. Anybody else want to give it a shot? Yeah. Right. Right. Okay. Yeah, so if we start applying this rate continuously, then after a little bit of time, what happened to the wound? It's smaller, right? So then we're taking a percent of a smaller value each. So as it shrinks, and you keep applying the same continuous rate to a shrinking volume, the overall effect then is to take less and less of an amount each time. So that compounds over to the idea that over the whole course of over one whole day, it only goes down 12.3. Because in that first day, the total size of the wound is shrinking. So you're taking a smaller value. By taking the same percent of a smaller and smaller value, you get a smaller and smaller value. And so the overall effect of that is to go down less than 12.3, or less than 13.16, actually 12.3%. Okay, where are we at? Okay, so let's just, in 73, any questions on 71? Anybody have a question? Okay, in 73, first you're going to get, it gives you two populations, in 1970 and 2000. So what can you start by getting? What's the first thing we can get easily? Which growth factor? 30. So this is 30 years. So in 30 years, the multiplier would be 9765 over 3562. So this is the number you'd multiply 3562 by to get 9765. That's our 30-year growth factor. What is it?
2.74.
Awesome, 2.74. So the question is, how do we get the 1-year growth factor? So this is the 30-year growth factor. Divide by 30. This is the 30-year growth factor. The 1 year will be? Better know this. The 1/30th. That's a small number. What is it? 1.034. Okay? Percent, actual percent change. 3.4% increase per year. I'm going fast. Am I right? Is this, with those of you who did this, is this right? Okay? So then the question is, if I want to rewrite this, so then I'm looking at per year, initial value A times this. If I wanted to write this as A e to the R in the continuous form, how could I get that continuous rate? 1.034 equals e to the R. Well, how am I going to solve for that R? How am I going to get that R? Yeah, it's an exponent. It's the exponent of e that gives 1.034. That's what natural log is. Natural log is the exponent of e that gives that result. So the continuous rate is? This ln is 0.0 what? 33?
Yes.
Okay, so the continuous rate then is 3.3%, which is not the true growth. The true growth is the 3.4% per year. Have a great break. Be safe. Homework for Wednesday is posted.
Mark, can you put the, are we doing it now, or are we still waiting half an hour?
Can you just come down?
I saw you had it up there.
The slide from Wednesday?
Yeah, you put
Let
it
me
up.
just leave this up for a moment for
Okay.
students to get, and just in like 30 seconds I'll put it up.
Sure. You're right. I didn't get that, and I was trying to rewrite it when you put that. I saw that you popped that slide back up, so I was trying to take
I
better
was scared
notes.
that I'd lost it.
This one's these examples I wasn't following with because I'm not getting that part. So I need to reread and do some more. Every time I have problems, I go through that book and do stuff you don't assign. And sometimes it does. Sometimes it pounds it into my, and then if not, I'll.
Well,
ask
the thing
you
about
or
this
him.
is it's combining everything we've done in this module. You have to know everything and have it all.
Well, that's
at your
where
disposal.
I'm stumbling right there. I mean, I took the notes, like I said, they're in here.
Okay, it's just, yeah. This thing right here. Is this what you mean?
Yeah, that one. Cool. Wait, just
I
go
forgot to ask,
re-jot
on
that down.
Tuesday, are your office hours closed because it's 12:30?
Yeah, I won't have
Yeah.
Tuesday office
So
hours,
Thursday, yeah.
but I will have Thursday.
Have a good one.
Question for you.
Yeah.
As far as the negative decreasing growth factor for the continuous, how come it's smaller and smaller? Like the
Yeah, it's a tough idea.
yeah.
So we got it to K, right? So like, so e to the negative, some other example.